Hello everyone. In this video, we will study the complete course in spectroscopy. You all know very well that spectroscopy is a vast subject and cannot be completed in one video. So, in this video, we will study general features of spectroscopy and UV spectroscopy. We will study the topic in the most popular method of learning, which is conversational method or question-answer method. Let us start with important solved questions of general spectroscopy, UV spectroscopy, IR spectroscopy, and NMR spectroscopy. The first question is, what is spectroscopy? And what are the main types of spectroscopy? The answer to this question is very simple. Spectroscopy is the study of the interaction between matter and electromagnetic radiation. It involves analyzing how different types of matter absorb, emit, or scatter light at various wavelengths to determine their composition, structure, and other properties. The main types of spectroscopy include absorption spectroscopy, example UV visible, IR, microwave. Emission spectroscopy, example flame emission, fluorescence. Raman spectroscopy. NMR spectroscopy. Mass spectroscopy. X-ray spectroscopy. The second question is, describe the electromagnetic spectrum. The answer to this question is very simple. The electromagnetic spectrum represents all types of electromagnetic radiation, ranging from gamma rays, short wavelength, high energy, to radio waves, long wavelength, low energy, arranged in increasing or decreasing order of wavelength, frequency or energy. It includes gamma rays, X-rays, ultraviolet, UV, light, visible light, infrared, IR, radiation, microwaves, and radio waves. The third question is, what is the significance of a spectrum in spectroscopy? The answer to this question is very simple. A spectrum is a graphical representation of the amount of light absorbed, emitted, or scattered by a sample as a function of wavelength or frequency. It provides crucial information about the energy transitions in a substance and is used to identify its molecular or atomic structure. The next question is, explain the difference between absorption and emission spectroscopy. The answer to this question is very simple. Absorption spectroscopy measures the wavelengths of light absorbed by a substance as it transitions from a lower to a higher energy state. Emission spectroscopy, on the other hand, measures the wavelengths of light emitted by a substance as it transitions from a higher to a lower energy state. In absorption spectroscopy, light of a specific wavelength is absorbed by the sample, causing an electron to move from a lower energy state, which is called ground energy state or simply ground state, to a higher energy state, which is called excited energy state or simply excited state. The amount of light absorbed at each wavelength is recorded. In emission spectroscopy, the sample is first excited, often thermally, to a higher energy state, and when it returns to the lower energy state, which is also called ground state, it emits light, which is then measured. The next question is, what is a continuous spectrum? The answer to this question is very simple. A continuous spectrum shows all wavelengths of light within a given range with no gaps. It is produced by a hot, dense object, such as a blackbody radiator, and does not contain discrete lines or bands. It is also called band spectrum, and there is no space between the bands. The next question is, what is a line spectrum? The answer to this question is very simple. A line spectrum consists of distinct, sharp lines at specific wavelengths corresponding to the transitions between discrete energy levels in atoms or molecules. Line spectra are characteristic of gases or atoms in low-pressure environments. It is also known as discontinuous spectrum. The next question is, what is an excitation spectrum? The answer to this question is very simple. An excitation spectrum is obtained by measuring the intensity of emitted light as a function of the wavelength of excitation light. It provides information about the energy levels of the species being studied and is commonly used in fluorescence spectroscopy. The next question is, what is meant by atomic spectroscopy? The answer to this question is very simple. Atomic spectroscopy is a technique used to analyze the atomic composition of a sample by examining the light emitted or absorbed by its atoms. This method leverages the fact that atoms, when excited, emit or absorb specific wavelengths of light that are characteristic of the elements they contain. The next question is, what are the different types of atomic spectroscopy? The answer to this question is very simple. Types of atomic spectroscopy. We have following main types of atomic spectroscopy. Atomic absorption spectroscopy. It is abbreviated as AAS. In this spectroscopy, we measure the absorption of light by the free atoms in the gas phase. This technique is commonly used for quantitative analysis of metals in liquids. Atomic emission spectroscopy. It is abbreviated as AES. In this spectroscopy, we detect the light emitted by excited atoms as they return to their lower energy states. This technique is commonly used for analyzing the composition of materials and detecting metals. Atomic fluorescence spectroscopy. It is abbreviated as AFS. This spectroscopy involves excitation of atoms by light and measurement of fluorescence emitted. It is highly sensitive and is used for trace metal detection, which means metals that are present in trace or very small amounts. The next question is, what is meant by molecular spectroscopy? The answer to this question is very simple. Molecular spectroscopy is a technique used to study molecules by analyzing the interaction of electromagnetic radiation with matter. It focuses on the energy transitions that occur at the molecular level primarily through vibrations, rotations, and electronic transitions within molecules. This method provides valuable information about the structure, dynamics, and chemical composition of molecules. The next question is, what are different types of molecular spectroscopy? The answer to this question is very simple. Different types of molecular spectroscopy. There are many types of molecular spectroscopy. The most common types that are studied by undergraduate students are given as: first of all, infrared IR spectroscopy studies the vibrations and rotations of molecules. Molecules absorb infrared light, causing changes in their vibrational and rotational energy states. Widely used for identifying functional groups in organic compounds. Second one is Ultraviolet visible UV-vis spectroscopy analyzes electronic transitions between molecular energy levels. Molecules absorb ultraviolet or visible light, leading to electron excitation. Commonly used in studying conjugated systems, chromophores, and determining concentrations of compounds. Most commonly and most informative is nuclear magnetic resonance (NMR) spectroscopy studies the magnetic properties of atomic nuclei in a magnetic field. Provides detailed information about the molecular structure, especially in organic compounds. Used extensively in chemistry for determining the structure of complex molecules. The next question is, what are the key regions of the electromagnetic spectrum used in spectroscopy? The answer to this question is very simple. The key regions used in spectroscopy are the ultraviolet UV region 10 to 400 nanometers, visible region 400 to 700 nanometers, infrared IR region 700 nanometers to 1 millimeter, and microwave region 1 millimeter to 1 meter. Each region is used for different types of spectroscopy, depending on the energy transitions involved. The next question is, define wavelength and frequency. The answer to this question is very simple. Wavelength is the distance between two successive peaks, also called crests, or grooves, also called troughs, of a wave, typically measured in meters or nanometers, nm. Frequency is the number of wave cycles that pass a point per second, measured in hertz, hertz. Wavelength and frequency are inversely proportional. As wavelength increases, frequency decreases. The next question is, how is the energy of a photon related to its wavelength and frequency? The answer to this question is very simple. The energy of a photon is directly proportional to its frequency and inversely proportional to its wavelength. The relationship is described by the equation E is equal to h multiplied by nu is equal to h into c divided by lambda, where E is the photon energy, h is Planck's constant, nu is the frequency, c is the speed of light, and lambda is the wavelength. The next question is, what is meant by quantized energy levels in atoms and molecules? The answer to this question is very simple. Atoms and molecules have specific, discrete energy levels. Electrons in an atom or molecule can only occupy these energy levels, and the transitions between them involve absorbing or emitting fixed amounts of energy, quanta. This leads to the formation of characteristic spectra. The next question is, what is the Beer-Lambert law and how is it applied in spectroscopy? The answer to this question is very simple. The Beer-Lambert law states that the absorbance of light passing through a substance is directly proportional to the concentration of the substance and the path length of the light through the material. Mathematically, A is equal to epsilon multiplied by C multiplied by L, where A is the absorbance, epsilon is the molar absorptivity, C is the concentration, and L is the path length. It is used in quantitative analysis to determine the concentration of a sample based on its absorbance. The next question is, what is the molar absorptivity, epsilon, in ultraviolet and visible spectroscopy? The answer to this question is very simple. Molar absorptivity, which is also called the molar extinction coefficient, is a measure of how strongly a substance absorbs light at a given wavelength. It is used in the Beer-Lambert law and is expressed in units of liter per mole per centimeter. Higher epsilon values indicate strong absorption. The next question is, how does a spectrometer work? The answer to this question is very simple. A spectrometer is an instrument that measures the intensity of light at different wavelengths. It typically consists of a light source, a sample holder, a wavelength selector, such as a prism or diffraction grating, and a detector. The sample absorbs or emits light, and the spectrometer separates this light by wavelength and measures its intensity. The next question is, what role does the detector play in a spectroscopic instrument or a spectrometer? The answer to this question is very simple. The detector measures the intensity of light after it has passed through or interacted with the sample. The most common detectors include photomultiplier tubes, PMTs, charge-coupled devices, CCDs, and photodiodes. They convert light into an electrical signal, which is then processed to generate a spectrum. The next question is, what is a monochromator and how is it used in spectroscopy? The answer to this question is very simple. A monochromator is a device used to select a narrow band of wavelengths from a broader range of light. It typically consists of a dispersive element like a prism or diffraction grating and adjustable slits to isolate specific wavelengths. In spectroscopy, a monochromator is used to direct a specific wavelength of light onto the sample. The next question is, explain the term spectral resolution. The answer to this question is very simple. Spectral resolution refers to the ability of a spectrometer to distinguish between two closely spaced wavelengths or frequencies. Higher resolution means better separation of overlapping spectral features, which is essential for accurate analysis of complex samples. The next question is, how does the resolution of a spectrometer affect the quality of a spectrum? The answer to this question is very simple. The resolution of a spectrometer determines its ability to distinguish between two closely spaced wavelengths or frequencies. Higher resolution allows for finer details in the spectrum, which is important for distinguishing between closely related compounds or fine structural features. The next question is, what is the importance of band intensity in a spectrum? The answer to this question is very simple. Band intensity in a spectrum is related to the concentration of the absorbing or emitting species and the probability of the transition. In quantitative spectroscopy, the intensity of absorption or emission bands can be used to determine the concentration of a substance in a sample. The next question is, how do rotational, vibrational, and electronic transitions differ in spectroscopy? The answer to this question is very simple. All the three types of spectroscopies follow the same principle and are normally studied in the form of absorption spectroscopies. The fundamental differences between these three types of spectroscopies are as follows. Rotational transitions occur at low energy, microwave region and involve the rotation of molecules. Vibrational transitions occur at higher energy, IR region and involve changes in the vibrational energy levels of molecules. Electronic transitions occur at even higher energy, UV visible region, and involve the excitation of electrons from one energy level to another. The next question is, what are the common sources of radiation used in spectroscopy? The answer to this question is very simple. Common sources of radiation required for different types of spectroscopies include: for UV and visible spectroscopy, the sources of radiation are deuterium lamps for UV spectroscopy and tungsten halogen lamps for visible spectroscopy. For IR spectroscopy, the sources of required radiations are Glauber sources, silicon carbide, and Nernst-Glavers. For microwave spectroscopy, the main source of microwave radiation are magnetrons. For X-ray spectroscopy, the main source of required radiations are X-ray tubes. The next question is, describe the concept of selection rules in spectroscopy. The answer to this question is very simple. Selection rules determine which transitions between energy levels are allowed or forbidden based on quantum mechanical principles. These rules depend on factors such as the change in angular momentum and the symmetry of the molecule. For example, in ultraviolet and visible spectroscopy, transitions between singlet and triplet states are forbidden. The next question is, define selection rules and describe spin selection rules applicable in UV spectroscopy. The answer to this question is very simple. From the name it is very clear that these are the rules that help us to make a decision or a selection. The selection rules in UV spectroscopy help determine whether an electronic transition is allowed or forbidden. The two main rules are: spin selection rule, transitions between electronic states must not involve a change in spin multiplicity. Delta S is equal to 0, meaning the total spin quantum number should remain the same. Transitions like singlet to singlet or triplet to triplet are allowed, but singlet to triplet are forbidden. The next question is, describe Laporte selection rule that are applicable in UV spectroscopy. The answer to this question is very simple. Laporte selection rule. This rule applies to centrosymmetric molecules and states that transitions between states of the same orientation are allowed and other transitions are forbidden. This explains why the transitions between sigma and sigma star, as well as pi and pi star molecular orbitals are allowed, and all other types of transitions are forbidden. The next question is, how does molecular symmetry affect the spectra of molecules? Molecular symmetry determines which transitions are allowed or forbidden in spectroscopy. Highly symmetric molecules may have fewer allowed transitions, leading to simpler spectra, whereas asymmetrical molecules typically show more complex spectra with more absorption bands. The next question is, what is the Doppler effect in the context of spectroscopy? The answer to this question is very simple. The Doppler effect refers to the shift in the frequency, and thus wavelength, of light due to the relative motion between the light source and the observer. In spectroscopy, this effect can cause broadening or shifting of spectral lines if the sample or observer is in motion. The next question is, how does temperature affect the spectral lines in spectroscopy? The answer to this question is very simple. Temperature affects the population of atoms or molecules in different energy levels according to the Boltzmann distribution. Higher temperatures increase the population of excited states, which can broaden spectral lines and increase the intensity of emission spectra. The next question is, why is it important to calibrate a spectrometer? The answer to this question is very simple. Calibration ensures that the spectrometer accurately measures wavelengths and intensities. Calibration is performed using reference standards with known spectral characteristics. Without calibration, measurements could be inaccurate, leading to erroneous data. The next question is, how do molecular vibrations influence spectroscopic measurements? The answer to this question is very simple. Molecular vibrations, such as stretching and bending, absorb specific frequencies of IR radiation. These vibrations correspond to certain bonds and functional groups, allowing for the identification of molecular structure in IR spectroscopy. The next question is, what is a reference spectrum and how is it used? The answer to this question is very simple. A reference spectrum is a baseline measurement of a substance. A reference spectrum is a baseline measurement of a substance with known properties or a blank sample. It is used to subtract background noise or interferences from the sample's spectrum, ensuring more accurate measurements. The next question is, how do absorption bands relate to molecular structure? The answer to this question is very simple. Absorption bands in a spectrum correspond to specific energy transitions within a molecule, such as electronic, vibrational, or rotational transitions. These bands provide information about the types of bonds and functional groups present in the molecule, aiding in its structural identification. The next question is, what is ultraviolet and visible spectroscopy? The answer to this question is very simple. UV visible spectroscopy is a technique that measures the absorption of ultraviolet and visible light by a sample. The absorption corresponds to electronic transitions between energy levels in molecules, and the resulting spectrum provides information about the electronic structure of the sample. The next question is, how are the electronic transitions observed in ultraviolet and visible spectroscopy? The answer to this question is very simple. In ultraviolet and visible spectroscopy, electronic transitions occur when electrons in a molecule absorb photons and are excited from a lower energy level, ground state, to a higher energy level, excited state. These transitions usually involve the promotion of electrons from bonding or non-bonding orbitals to antibonding orbitals. The next question is, what is the difference between sigma to sigma star, pi to pi star, and n to pi star transitions? The answer to this question is very simple. Sigma to sigma star transitions involve the excitation of electrons from a sigma bonding orbital to an anti-bonding sigma orbital. These transitions require high energy, typically in the UV range. Pi to pi star transitions involve the excitation of electrons from a pi bonding orbital to an anti-bonding pi orbital. These are common in molecules with conjugated double bonds and occur in both the UV and visible ranges. N to pi star transitions involve the excitation of non-bonding, lone pair, electrons to an anti-bonding pi orbital. These transitions also occur in the ultraviolet region but at lower energy than pi to pi star transitions. The next question is, what do you mean by the term forbidden transitions? Forbidden transitions are those that violate the selection rules, making them less likely to occur. These transitions have low probability but can still occur due to phenomena like vibronic coupling, which slightly relaxes the selection rules. N to pi star transitions, in molecules with lone pairs like carbonyl groups, are often considered forbidden but can still be weakly observed. The next question is, what do you mean by the term allowed transitions? The answer to this question is very simple. Allowed transitions, in ultraviolet spectroscopy, electronic transitions between molecular orbitals are governed by selection rules, which determine whether a transition can occur with significant probability. For a transition to be allowed, it must satisfy certain quantum mechanical selection rules, such as changes in angular momentum, change, or no change in dipole moment, change, or no change in spin multiplicity, parallel, or non-parallel orientation of the molecular orbitals, or energy levels between which the electronic transition will take place. In ultraviolet visible spectroscopy, sigma to sigma star, pi to pi star transitions, example in conjugated systems, are allowed. However, N to pi star transitions which are actually forbidden are also observed and are often confused with the allowed transitions. The next question is, why forbidden transitions are observed in ultraviolet spectrum? This is a very important question, and the answer to this question is very simple. Forbidden transitions can still be observed in UV spectra because real molecules are not ideal systems, and selection rules are often slightly relaxed. Reasons include vibronic coupling. In many molecules, vibrational modes can couple with electronic transitions, slightly relaxing the selection rules, making forbidden transitions observable, albeit with lower intensity. Spin-orbit coupling. In heavier atoms, spin-orbit coupling can mix singlet and triplet states, allowing forbidden transitions to occur with a weak signal. Symmetry breaking. In real molecules, perfect symmetry often doesn't exist due to molecular vibrations or environmental effects, allowing forbidden transitions to be partially allowed. The next question is, what is meant by the term absorbance maxima in ultraviolet and visible spectra? What is its significance? The answer to this question is very simple. The absorbance maxima correspond to the wavelength at which a substance absorbs light most strongly. This provides information about the electronic transitions within the molecule and can be used to identify the chromophore and its surrounding environment. The next question is, what is meant by chromophore and what is the role of chromophores in ultraviolet and visible spectroscopy? The answer to this question is very simple. Chromophores are the parts of a molecule responsible for absorbing light in the ultraviolet and visible region. They typically contain conjugated systems of double bonds or aromatic rings where electronic transitions such as pi to pi star and N to pi star occur. The presence of chromophores gives rise to the absorption peaks seen in an ultraviolet and visible spectrum. The next question is, what is meant by the term oxochrome and what is their role in ultraviolet and visible spectroscopy? The answer to this question is very simple. Oxochromes are groups attached to chromophores that modify the absorption properties of the chromophore. Oxochromes can cause shifts in the wavelength of maximum absorption and influence the intensity of absorption bands. Examples include hydroxyl OH and amino NH2 groups. The next question is, what is a bathochromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Bathochromic shift, it is also known as red shift, refers to a shift of the absorption maximum to a longer wavelength, lower energy. This results in the absorption of light at longer wavelengths, often perceived as a red shift. Causes. The common causes include factors like solvent polarity, increased conjugation, example addition of double bonds or aromatic rings, and changes in molecular structure can cause a bathochromic shift. It occurs because the energy gap between the ground and excited states decreases, allowing the molecule to absorb lower energy light. The next question is, what are the factors for bathochromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Bathochromic shift or red shift is caused due to many factors. However, most commonly it is caused by increased conjugation, example extended pi systems. Solvent effects, especially solvents with higher polarity stabilize the excited state more than the ground state. Electron donating substituents that stabilize the excited state. The next question is, what is a hypsochromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Hypsochromic shift, it is also known as blue shift. It refers to a shift of the absorption maximum to a shorter wavelength, higher energy. This results in the absorption of light at shorter wavelengths or a blue shift. Causes. The common causes include factors such as decreased conjugation, increased molecular rigidity, and the presence of electron withdrawing groups can lead to a hypsochromic shift. It happens when the energy gap between the ground and excited states increases, requiring higher energy, shorter wavelength, light for absorption. The next question is, what are the factors for hypsochromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Hypsochromic shift or blue shift is caused due to many factors. Some of the common factors responsible for hypsochromic shift or blue shift are decreased conjugation or disruption in conjugation, electron withdrawing groups, less polar or non-polar solvents that stabilize the ground state more than the excited state. The next question is, what is a hyperchromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Hyperchromic shift, this refers to an increase in the intensity of absorption or absorbance. The absorption peak height becomes higher, indicating that more light is being absorbed by the sample. Causes. The common causes include a hyperchromic effect can occur when there is an increase in the number of chromophores, light-absorbing groups, or when the molecular environment allows more efficient electronic transitions. The next question is, what are the factors for hyperchromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Hyperchromic shift, or increase in intensity of the peak of the transition, can be caused due to a number of factors. However, Most commonly, it is caused by increase in the number of absorbing centers or chromophores. Solvent effects that enhance transition probability. Structural modifications that make electronic transitions more likely, which means increases the probability of transition. For example, molecular collision which make the electronic level parallel to each other. The next question is, what is a hypochromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Hypochromic shift. This refers to a decrease in the intensity of absorption or absorbance in a spectrum. In ultraviolet visible spectroscopy, it means that the absorbance of a molecule decreases, leading to a lower peak height in the spectrum. Causes. The most common causes include: a hypochromic effect can occur due to structural changes in a molecule, such as increased rigidity, or the presence of groups that limit electronic transitions. It can also happen due to interactions with solvents that reduce the probability of absorption. The next question is, what are the factors for hypochromic shift in ultraviolet and visible spectroscopy? The answer to this question is very simple. Hypochromic shift, or decrease in intensity of the peak of the transition, can be caused due to a number of factors. However, most commonly it is caused by structural changes that decrease the efficiency of electronic transitions, steric hindrance that affects molecular geometry and reduces absorption intensity, formation of hydrogen bonds that alter electronic structure. The next question is, why do bands appear in ultraviolet spectrum? This is a very important question. The answer to this question is very simple. In ultraviolet visible spectroscopy, bands rather than sharp peaks are typically observed. This occurs due to several factors. Vibrational and rotational transitions. Electronic transitions are accompanied by a multitude of vibrational and rotational transitions, leading to closely spaced energy levels. This results in the broadening of absorption bands rather than sharp peaks. Solvent effects. Solvent molecules can interact with the absorbing species, causing small variations in energy levels and broadening the absorption spectrum. Molecular motion. The movement and interactions of molecules in a solution lead to inhomogeneous broadening, which further spreads out the absorption signals. Franck-Cordon principle. According to this principle, during an electronic transition, the nuclear positions don't change instantly, leading to multiple vibronic transitions, which result in broad bands. The next question is, how do solvents affect ultraviolet and visible spectra? The answer to this question is very simple. Solvents can influence the position and intensity of absorption bands in ultraviolet and visible spectroscopy due to solute-solvent interactions, polarity, and hydrogen bonding. For example, polar solvents can stabilize excited states more than nonpolar solvents, leading to shifts in the absorption wavelength, which is also known as solvatochromism. The next question is, what is the ultraviolet cutoff in solvents, and why is it important? The answer to this question is very simple. The ultraviolet cutoff is the wavelength below which a solvent absorbs ultraviolet light strongly, making it unsuitable for use in ultraviolet and visible spectroscopy. It is important to choose solvents with ultraviolet cutoffs below the region of interest to avoid interference with the sample's absorption. The next question is, What are the applications of ultraviolet and visible spectroscopy in chemical analysis? The answer to this question is very simple. Ultraviolet visible spectroscopy is widely used for qualitative and quantitative analysis in chemistry. Applications include identifying compounds, studying reaction kinetics, monitoring chemical changes, and determining the concentration of solutes in solutions. The next question is, how does ultraviolet and visible spectroscopy aid in determining molecular concentration? The answer to this question is very simple. Using the Beer-Lambert law, ultraviolet and visible spectroscopy allows for the determination of molecular concentration by measuring absorbance at a specific wavelength. The concentration is directly proportional to the absorbance, provided the molar absorptivity and path length are known. The next question is, how is ultraviolet and visible spectroscopy applied in biochemistry? The answer to this question is very simple. Ultraviolet visible spectroscopy is commonly used in biochemistry to study proteins, nucleic acids, and other biomolecules. It is used to determine the concentration of DNA and RNA, monitor protein folding, and analyze enzyme kinetics by measuring changes in absorbance over time. The next question is, how do transition metals absorb ultraviolet and visible light? The answer to this question is very simple. Transition metals absorb ultraviolet and visible light due to d-d electronic transitions, where an electron is excited from one d orbital to another. These transitions depend on the oxidation state of the metal, the ligand field, and the geometry of the complex, leading to characteristic absorption bands in the visible region. The next question is, how is ultraviolet and visible spectroscopy used to study reaction kinetics? The answer to this question is very simple. Ultraviolet visible spectroscopy can be used to monitor changes in absorbance over time as a reaction progresses. By measuring the absorbance of reactants or products at specific wavelengths, the rate of the reaction can be determined and kinetic parameters such as rate constants can be calculated. The next question is, how is ultraviolet and visible spectroscopy applied in pharmaceutical analysis? The answer to this question is very simple. In pharmaceuticals, ultraviolet and visible spectroscopy is used for the identification and quantification of active pharmaceutical ingredients, APIs, and excipients. It is also used to monitor drug stability, degradation, and purity during quality control testing. The next question is, what are the limitations of ultraviolet and visible spectroscopy? The answer to this question is very simple. Limitations include low specificity. Ultraviolet and visible spectra often lack fine structure, making it difficult to distinguish between similar compounds. Sensitivity to impurities. Ultraviolet and visible spectroscopy can be affected by the presence of contaminants that absorb in the same wavelength range. Limited to compounds with chromophores, non-chromophoric compounds cannot be analyzed without modification.